On Friday, the 4-person crew of Artemis II will hit the Earth's atmosphere at roughly 25,000 miles per hour. To understand that scale, that is about 32 times the speed of sound. If the Orion capsule were to fly directly into the atmosphere at that velocity, the heat and G-forces would likely exceed the structural limits of the spacecraft and the biological limits of the crew. Unlike the International Space Station, which returns from low Earth orbit at around 17,000 miles per hour, Orion is coming from the Moon. That extra 8,000 miles per hour doesn't just add a little heat, it increases the thermal load exponentially. In this autopsy, we're looking at this Skip Reentry maneuver, the high-stakes physics trick NASA is using to keep this crew alive. Standard reentries are a single, continuous descent, but for Artemis II, Orion will perform what engineers call a skip. Imagine skipping a stone across a pond. The capsule will hit the upper atmosphere, use its lift-to-drag ratio to bounce back up into space briefly, and then perform a second, final re-entry. Why do this? 2 reasons: range and G-load. First, the skip allows NASA to precisely target a splashdown point near San Diego, regardless of where they enter the atmosphere. Second, it breaks the heat and deceleration into 2 smaller pulses. This keeps the G-forces at a level the human body can actually sustain after 10 days in microgravity. If this skip timing is off by even a fraction of a degree, the ship could either skip away into a permanent orbit or dive too deep and incinerate. To survive the 5,000-degree plasma field, the base of the Orion capsule is covered in a material called Avcoat. This isn't just a shield, it's an active chemical system. Avcoat is an ablative material. As it heats up, it's designed to char and flake away, physically carrying the heat away from the spacecraft. We need to compare this to SpaceX's Starship. While Elon Musk's team uses reusable ceramic tiles, NASA chose a single-use ablative shield for Orion because it's more predictable at the extreme velocities of a lunar return. During Friday's re-entry, over 200 pounds of this material will literally vaporize. We'll be watching the telemetry specifically for thermal soak, the moment after re-entry when the heat could potentially bleed through the structure and cook the cabin electronics. Once the capsule survives the heat, it still has to slow down from 300 miles per hour to 20 miles per hour for splashdown. This is handled by a sequence of 11 different parachutes. First, the forward bay cover is jettisoned, then 2 drogue chutes deploy to stabilize the capsule. These are followed by 3 pilot chutes that pull out the 3 massive main chutes. Each main chute is the size of a football field. But here's the technical failure point. If one of the 3 main chutes fails to inflate, the capsule will hit the water at a velocity that could cause structural compromise or internal injury to the crew. We saw a similar parachute anomaly during the Boeing Starliner tests, so the Navy recovery teams will be tracking the canopy inflation metrics in real time. Artemis II isn't just a return to the Moon, it's a validation of high-energy re-entry. The data gathered Friday, the vibration, the ablation rate, and the skip timing, will dictate the design of the Mars return vehicle. If Orion splashes down safely within the target zone, it proves that our current thermal protection models are ready for the next decade of deep space travel. This is NASA Community News. Subscribe for the full splashdown analysis.